What is the voltage in between capacitors? Namely, 3 capacitors. So we have one terminal, capacitor 1, C1, and then capacitor 2, terminal 2, capacitor 3, terminal 3. Very beautiful setup. And the question is, what is the voltage at point P? We are given the voltages V1, V2, V3 at these terminals, and we're given the capacitances C1, C2, C3. What is VP? This was a competition problem, physics competition, long ago. And it seems really easy, right? You say to yourself, wow, I just used this formula, Q equals V times C. Ta-da! But let's think about this. And the more you think about it, the more doubts set in. Yes, okay, V. What V? Where V? We're given V1, we're given V2, V3, we're given the voltages at the terminals. We're not actually given the voltage across the capacitors. And here, Q. What do we mean by Q? Is it the voltage on this plate? Is it the voltage on this plate? Or is it the voltage on both plates? Or all of them? Or sorry, the charges? Q, is it the charges on all plates, or some plates, or one plate? What is Q? So the doubts creep in and we think, maybe it's not that easy. It is easy, you just have to think about it. And in the process, you will understand capacitors a lot better. Okay, let's make a little simplified drawing. Terminal 1 and 2, capacitor C. All right, I want to know what this charge is and what this charge is. Let's say this is high and this is low voltage. So if I do V1 minus V2 and multiply by C, this is positive. Okay, so positive is going to induce this charge here. Well, no, it's going to make this positive, and this negative will be induced on the other plate. Okay, so this gives us Q1, the charge on plate 1. What about if we want the charge on plate 2? Well, if we reverse this, this is now negative, so if we multiply this out, we get a negative charge. That has to be this charge here. This one must be Q2. Now, Q1 plus Q2 has to be 0 because there is nowhere for the charge to go. This is like an open circuit. There's no current flowing anywhere. So whatever charge is on this plate and whatever charge comes on this plate, it's got to be, the total has to be 0. Just think about it. There's no way for charge to get into this system and no way for charge to get out of it. So by conservation of charge, the two must give you 0. And if you plug these things in, you'll see, yeah, it's true. Okay. Now I want you to consider the opposite case. Take the minus, put it here, put a plus here, do the same calculation, and you'll see, yeah, it also works. So we have our convention. If you want the charge on this plate, you start with this terminal here and subtract this terminal. You want the charge on this plate, you start with the nearest terminal here and take this first, then subtract that one. That's how the convention works. Okay, great. Now, let's do a little bit more complex example. Okay, we have terminals 1, 2, and point P, C1, C2, and I want to find out the voltage in the middle. Right, now let's isolate this element here, this piece of the system. Look, it's 2 plates. It's not connected to anything. This is empty space here, or dielectric. There's no connection by wire to anything outside. So whatever charge is on this plate has to be exactly equal and opposite to the charge on this plate. The two have to sum to 0. because there is no way for charge to get in here, into this central element here, and there's no way for charge to get out of there, so the total charge has got to be 0. That's the key to solving our problem. Looking at the inside, forgetting that these are capacitors, and just looking at this wires and plates on the inside and realizing that this is an isolated system, so the charge has to be conserved. No matter where the charge goes, the sum of all the charges is going to be 0. Okay? Right, so let's calculate now Q1. Q1, I use my convention. I start with P, VP, and subtract V1. VP minus V1 times C1. And Q2 is, again, I want Q2 is this plate here. This is Q2. I want the charge on that plate, Q1 charge on that plate. So I start with P according to our convention, okay? So VP minus V2, C2. And now I add them together, I get 0. VP minus V1, C1 plus VP minus V2, C2. Got to give me 0, right? And if I expand all of this, I get VP equals C1 V1 plus C2 V2 over C1 plus C2. Now this is really beautiful and really amazing. Doesn't this remind you of center of mass? Like I've got two masses like this, M1, M2, and I have to find this fulcrum point here. Where does it balance? It's like that. Now, you should explore this analogy, okay? Because it's very interesting. There are many mechanical, electrical analogies, and I'm going to examine some of them in future videos. But this is kind of a really unusual one. Whoever thought of capacitors being like masses that are balanced? But we can take this idea further, and you see it works in this case too. So let's now take this problem, and again we're going to isolate these elements of our system in this circle. I'm going to take the stuff out from the center like this, you see, and this is going to be Q1, Q2, Q3, and my point here in the middle. Capacitor 1 and voltage 1 is up here. Capacitor 2, voltage 2 data here. Capacitor 3, voltage 3 data here at the terminal 3. Great. Now, this is isolated. It's not connected to anything. The fact that they're capacitors is kind of irrelevant to that. The total charge has to be 0 because there's no way for charge to have gotten in there or out of there. It was 0 to begin with. After we applied these voltages at the terminals, the charges moved around, but the sum is still 0. Okay, so what is Q1? Again, we use the convention, start at P and go subtract this guy, exactly as we have shown here. Memorize, well, don't memorize this, just really try to understand this. Do it over and over again till you understand where the plus and minus goes and how you can get which charge on which plate. Okay, so make sure you know that convention. So Q1 is going to be VP minus V1 times C1, and Q2 is VP minus V2 over C2, and Q3 is VP minus V3 C3. And when I add all these things together, it adds up to 0. I solve this system, and what do I get? Well, I get this. Let's write the whole formula down. Okay, VP minus VP C1 minus V1 C1 plus VP C2 minus V2 C2 plus V3 plus VP C3 minus V3 C3 equals 0. And I can now factor out all this VP stuff. Let's factor it out. I get C1 plus C2 plus C3, and I can bring all that other stuff to the other side. C1 V1 plus C2 V2 plus C3 V3, and lo and behold, let's write it up here. I get the solution. VP is C1 V1 plus C2 V2 plus C3 V3 over C1 plus C2 plus C3. That is amazing. Look at that. What does that remind you of? Yeah. Centroid or barycenter, right? You know, something like this. The centroid, you have masses and center of mass of a triangle, or it's centroid of three masses, weighted average, centroid, and so here again we have a mechanical analogy for capacitors as this system of capacitors. It's really beautiful, and I want to explore this mechanical analogy further. Now, as you can see from all of this analysis, okay, you understand now why this problem was chosen for a competition. It's elementary, but you cannot rely on just memorizing formulas of electronics. You have to understand the way things work a little bit more clearly than that in order to solve this problem. Okay, I thought this was a great problem. And why don't you do this version of it, okay? We have now something like this, okay? Why don't you go ahead and solve this as practice and explore that mechanical analogy a bit more. C2, C3, C4. So I'm given these voltages. I'm given V1, V2, V3, V4, and C1, C2, C2, C3, C4, and find VP in the center. What is this point here? Go ahead and do this problem. Okay, if you like capacitors, if you like this problem, click like, subscribe. I'll do more electronics problems. I'll try to choose interesting off-the-wall problems like this one. And I hope you enjoyed the video.